It is about time. So first of all, I would like to welcome everyone. Thanks for joining today for this VTS Young Professional Seminar Series seminar. And before we start, I would like to ask, do you hear us properly?
Yeah, yes.
Yes.
Okay, wonderful. So thanks a lot. We have today Dr. Baldomero. He is a research fellow at UWI Core Laboratory at University of Miguel Hernadez, UMH, in Spain. And the topic for today's talk is 5G NR V2X for connected and automated driving. And I'm happy to say that Dr. Baldo is one of those researchers who started in the very beginning of the V2X research about 12, 13 years ago. And I remember reading his paper in those days, even when I finished my PhD and joined Volvo. So because of Javier and his research group. So they have been doing quite a good work within Europe and of course contributing to the V2X research. So I would like to give the floor to Dr. Baldomero, and yeah, the floor is yours. Thank you.
Thanks a lot, Taimoor. Let me, yeah, now, thanks a lot again. This is Baldomero. I'm a senior researcher at the Universidad of Elche, as Taimoor has said. Today, I would like to share with you some of the research we are doing at our UWICORE laboratory as part of the PhD thesis of Alejandro Molina Galán that I'm co-supervising with together with Professor Javier González, who is the head of our research laboratory. As Taimoor has said, the talk would be about 5G new radio, V2X. I will mainly introduce what are the main functionalities that have been introduced with respect to its predecessor LTE V2X. Some studies that we are doing with regards to these novel functionalities that are being introduced. Okay. So as you might be aware of, 3GPP introduced in release 16 what is called 5G NR V2X. That is the first V2X standard based on 5G new radio air interface. This 5G new radio V2X has introduced novel functionalities in order to support connected and automated driving use cases that have more stringent requirements that in principle cannot be supported with the current V2X standard. The 5G new radio was first introduced and developed as part of the release 15, but this standard didn't include this cycling aspect. I mean, the direct communication between devices, vehicles in this case, and was limited to the UU communication, so uplink and downlink communication. So this makes this release 16 the first standard that supports 5G new radio V2X communication, both on cycling and UU interface. An important aspect that is defined in the 3GPP is that 5G New Radio V2X will not replace but complement LTE V2X, so that LTE V2X can be in charge of what we call in Europe day one services or basic services that rely on broadcast transmission, while 5G New Radio V2X support enhanced or Day 2 plus services with unicast, groupcast, and broadcast transmission. To complement LTE V2X, 5G New Radio introduces some new features both at the physical and MAC layer, including a much more flexible radio interface and new mechanism at the MAC layer, such as the revaluation mechanism that we will put more attention on at the end of this presentation, with the aim of having a higher efficiency and dealing with some of the inefficiencies detected in its predecessor LTE V2X technology. So the main objectives of this presentation is first summarize these novelties introducing 5G NR V2X for cycling communication that was the main focus of the Release 16, and also analyze how this technology, 5G NR V2X, can handle some of the inefficiencies of LTE V2X, and especially when vehicles transmit aperiodic traffic of variable size. To start with, let's talk about the operating band for 5G New Radio V2X. In principle, this technology can operate in these two frequency ranges that are called frequency range 1 and frequency range 2 based on the 3GPP terminology. This frequency range 1, as you can see, is more focused on the lower band below 7 gigahertz, while the frequency range 2 is more focused on the millimeter wave band, right, at higher frequencies. Although this is the case, so in principle, 5G NR V2X could work on these two frequency ranges. The main focus on Release 16 was on the lower frequencies, and Release 17 has been focusing more on this second frequency range. Actually, for the frequency range 1, 3GPP considers that 5G NR V2X can operate in these 4 bands included in the frequency range 1. Let me focus mainly on these 2 bands, what are called the N3038s, that is only reserved for new radio V2X communication when it is used for cycling, for V2X cycling services. Otherwise, this band is utilized for UU-based cellular communication. And then another band that you might be familiar with is the unlicensed ITS band around 5.9 gigahertz that is also available for 5G New Radio V2X. With regards to this ITS band, my most updated knowledge, I apologize if I'm not fully correct because this is changing lately, is that in Europe, for instance, this ITS band is defined to be technology neutral, while in other regions such as the US and China, they are reserving part of this spectrum for what is defined in the spectrum regulation as cellular V2X, which mainly refers to LTE V2X. I'm highlighting this because an important aspect for also in the standardization process of 5G V2X was the coexistence between 5G V2X and Elche V2X. It is defined that it is not possible that these two technologies coexist in the same channel. Using the same radio resources, because these two technologies are gonna rely on a different resource pool. So in those regions that are allocating the ITS spectrum on a technology basis, should consider whether to further split the ITS band in order to identify the usage of LTE V2X and 5G new radio V2X. The coexistence of the two technologies was considered as part of the standardization process of 3GPP, first at a device level and also at a network level. In a device level, what is called in-device coexistence, the vehicle themselves are the one managing this coexistence. And the main challenge is how to coordinate the two technologies so that the available transmission power is limited to the maximum one, right, at each point in time. So a first solution to address this issue is based on time division multiplexing. We might think that it's the simple case in the sense that at each point in time, each technology will have the spectrum or the resources available to perform the transmission so that they don't collide each other. The simpler case would be what is called a long-term solution that allocate subframes, in this example, for the different technologies, and without specifying whether the vehicles will transmit or receive in these specific subframes. So this is a simpler allocation that solves the problem that might not be efficient in the sense that this allocation, long-term allocation, might not fit to the needs of the two technologies to accommodate the traffic that the vehicles are generating. A more sophisticated solution that requires further and advanced coordination between the vehicles would be this short-term solution, where, as you can see in this example, subframes, or even at a lower level, as we are going to see, new radio V2X can operate below the subframe level of LTE V2X. Vehicles can coordinate to decide when each of them will transmit in each technology, and most importantly, the two technologies could be configured to receive at the same time, because the reception is not an issue. It's more on the allocation of the power and the mutual interference between the two technologies. An alternative that also allows vehicles to simultaneously transmit over both technologies is using a FDM solution. In this case, as it is shown in the figure, the available power must be shared between the two technologies. Although the standard actually only allows a simultaneous transmission with a static power assignment and using, an interband. So it is not supported that the two technologies are located in the same band. An alternative to the in-device coexistence is what is called cross-route control, where in this case, the network is managing when each technology is used. In particular, base station of each technology will manage the cycling radio resources of both technologies, but this solution is constrained to the fact that vehicles need to be under the cellular coverage, of course, because of the base station are the one managing the radio resources. As I said in the introduction, one of the key points of 5G and V2X is flexibility in the physical layer. This is a new aspect introduced in 5G new radio for V2X communication, although it has a frame structure similar to the one available for LTE V2X with a 10 millisecond radio frames and subframes of 1 millisecond. It introduced the concept of numerology already available for UU-based communication, but that was not present in LTE V2X, that allows an scalable number of slots in each subframe and also a different and scalable subcarrier spacing. For the case of LTE V2X, the only available numerology was numerology 0 that defines a subcarrier spacing of 15 kilohertz and a slot of 1 milliseconds. But 5G new radio V2X introduces for V2X communication 3 new numerologies that allows to configure the radio resources with different granularity, both in time and frequency, in order to cope with advanced and the needs of advanced V2X services. In particular, numerology 1 defines a subcarrier spacing of 30 kilohertz and a slot duration of 0.5 milliseconds. Numerology 2 increases the subcarrier spacing to 60 kilohertz and a slot duration of 0.25 milliseconds. And numerology 3, a subcarrier spacing of 120 kilohertz and a slot duration of 0.125 milliseconds. So with this, the result is that there are 4 different options for 5G new radio V2X to define what is called a resource block. It is a minimum unit to transmit information. It is defined by the slot duration and 12 subcarriers with this different subcarrier spacing. Another important aspect in 5G new radio V2X is that, as I said, it relies or it was defined taking into account inputs from the definition of new radio UU interface, where a carrier bandwidth can be divided into what are called different parts or different bandwidth parts. And in each of these bandwidth parts, it is possible to utilize a single numerology. So in new radio UU, the way to multiplex different traffic with different requirements is using multiple bandwidth parts. However, in new radio V2X, there is only one bandwidth part in each carrier. The same one is going to be used for all vehicles and with a single and the same numerology for all of them. This bandwidth part, instead, this bandwidth part, it is defined what is known as a resource pool that define the radio resources that are available for the cycling transmission, and that is defined in the time domain as a set of slots, not necessarily consecutive. There might be some gaps, as you can see here, that repeats over a resource pool period. And in the frequency domain, a set of physical resource blocks form what are called a subchannel, and different subchannel consecutive group to form this frequency domain of the resource pool. And one subchannel is the minimum unit that can be allocated to perform a data transmission. So since in new radio V2X for cycling communication, there is only one bandwidth part in each carrier, the way of multiplexing traffic with different requirements could be either using the numerology of the most restricted traffic, or using multiple carriers and then a bandwidth part in each of these carrier with different numerologies for each of these bandwidth parts. As I said, also 5G New Radio V2X introduces not only broadcast transmission, but also unicast and groupcast. In order to make more reliable transmission in these unicast and groupcast modes, it uses novel mechanisms such as the hybrid IRQ that is going to allow to retransmit some packets based on feedback received from the receiver. Actually, there is already some retransmission mechanism available in Elche V2X for broadcast transmission that relies on blind retransmission that perform a number of retransmission without any feedback. So this might be inefficient if some of the retransmission has been already received and the transmitter continues doing some transmission. Another functionality introduced in 5G V2X is the possibility to transmit cycling channel state information that is only available for unicast transmission, by which the receiver are going to provide some channel state information to the transmitter, and based on this information, the transmitter might adapt, for instance, the modulation and coding scheme that is being used. Other mechanism introduced is based on power control. What it's important to note here is that this power control is an open loop power control. So this is based on estimation. These are not real feedback received from the receiver to adapt the transmission power. And this adaptation in the power might be based on estimation based on downlink path loss from signal received from the base station, or cycling path loss from signal received from other receivers. Another different with respect to Elche V2X introducing 5G radio V2X is with regards to the report of cycling control information. So Elche V2X transmit this control information in a single stage, while NR-V2X uses for that two different stages. What is called first stage SCI, or cycling control information, includes information that receiver can use to decode the current packet, the current transport block, and also information that the transmitter is using to reserve future cycling transmission, so to reserve the resources of future transmission. While in the second stage SCI, it is included control information that is used to support the feedback mechanism that I introduced before. Another important difference between 5G NR-V2X and Elche V2X is in terms of synchronization. And here, while Elche V2X relies on satellites as well as information that can be received from the base station, 5G NR-V2X also support other sources of synchronization, such as a user called SyncRef UE that might act as a source of synchronization, and that is really useful for scenarios, for instance, where vehicles are out of coverage so that they cannot rely on the information transmitted by the base station, or when they are in tunnels and they cannot rely on satellite information. Now, if we move to the MAC layer, 5G NR-V2X defines two modes for the resource allocation, what are called mode 1 and mode 2. and that are the counterparts of mode 3 and mode 4 that are defined in Elche V2X. The mode 1 is the mode in which the base station assign and manage the cycling radio resources, and it defines two different mechanisms. One mechanism that is called dynamic grant, by which the vehicles, the user needs to request resources to the base station for the transmission of every single packet. And then there is also the configure grant mechanism, where the base station can pre-allocate in a semi-persistent manner cycling resources for the transmission of several packets. This pre-allocation of resources, what I call configure grant, as you can see in the figure, might have different periodicities and also different subchannels allocated in order to adapt or in order to meet the demands that different services might have. So an important aspect of this mode 2 is that since the resource allocation relies on the base station, it should be expected collision-free transmission, right? This is different than what we should expect when the resource allocation is performed based on mode 2, where the vehicles autonomously and in a distributed manner are gonna manage and select the cycling radio resources. For the mode 2, there are also two different mechanisms. One is called the dynamic scheduling, where the vehicles are going to select new resources for transmission of its packet. And if you are familiar with the Elche V2X mode 3, this is equivalent to the one-shot scheme used in Elche V2X. The second mechanism is called semi-persistent scheduling, and here the vehicles are going to select resources not for a single packet transmission like in dynamic, but for a number, reselection counter number of consecutive packets. And this is going to be done in a chain-like manner. So the transmission of each packet is going to announce the reservation of the resources to be used for the following, for the next packet transmission. And the time gap between the reserved resources is determined by a parameter called resource reservation interval, that for the case of 5GNR V2X introduces a higher granularity, especially in between 0 and 100 milliseconds. All this set of resource reservation interval is newly introduced in 5GNR V2X in order to accommodate advanced services that might require reservation with a higher granularity. And it is important to note that for the set of reselection counter consecutive transmission, the time gap between those resources is going to be the same. Is going to be given by this resource reservation interval. Let me elaborate a bit more on how the resource selection process works. For that, let me use this figure as an example, and let's consider that the resource selection process starts at this slot N. So if a vehicle is selecting resources, first it is going to identify what is called a selection window, that is here in the figure depicted in green, where the vehicle is going to look for candidate resources. And know that this selection window is defined by these two T1 and T2 parameter. But what is, I would say, more relevant is that the selection window is upper bounded by what is called the packet delay budget, so that any resource selected in this selection window meet the latency requirement of the packet to be transmitted. In addition to the selection window, the vehicle defines what is called sensing window, where it is going to look for reservation made by other vehicles, by other vehicles in this sensing window, and that might cause some conflicts in this selection window. Let me show you actually how this process works. This follows a two-step algorithm. The first one, the step one, the vehicle is going to exclude resources in this selection window based on first the reservation that other vehicles might be doing undetected in the sensing window. Imagine this is a transmission detected by another vehicle, and since this transmission is also reserving resources for future transmission with a RRI time gap, the vehicle can exclude these resources because this will be used by the vehicle at this point in time. Other resources that are also excluded include the ones that the vehicle could not detect because it was transmitting at this time as well. These are what is called the half duplex exclusion. And once this process, the step one finishes, the vehicle then look at the selection window and identify what resources are not excluded and randomly select one of the resources available. So this process, as I said, is completely random among the available resources, and the same resource will be used for consecutive reselection counted transmission with a time gap of RRI seconds, right? Since this process, as I said, is random and other vehicles might be selecting resources at the same time with overlapping selection window, there is a potential packet collision if two vehicles actually select the same resource. The 5GNR V2X has defined a mechanism that is aimed to cope with this packet collision. But before moving to this mechanism, let me briefly go to two additional mechanisms that are used in 5GNR V2X, that are the preemption mechanism that is used in 5GNR V2X to prioritize certain traffic. Basically, the idea here is that a vehicle with low priority traffic could execute the step one process, and if it detects that a vehicle with a higher priority traffic is using a resource that it has selected, then it will free the resource. Of course, the vehicle with a lower priority traffic could select a new resource by executing again the step two and selecting one among the free one. And another mechanism that is also used in 5GNR V2X and that was also present in LTE V2X is congestion control. Actually, the standard doesn't define a precise mechanism for congestion control, but rather it defines some metrics and possible countermeasures to reduce this channel load. The metrics defined include the channel busy ratio or the channel occupancy ratio, and possible countermeasures to reduce the channel load includes modifying the modulation and coupling scheme, the maximum number of subchannels that the vehicle could use to perform the transmission, the potential number of retransmission and also the maximum transmission power. As I said, and now I'm joining with the claim that I made before about the potential collision that might happen in the mode 2 of 5GNR V2X, and the mechanism introduced to actually cope with it. That is the reevaluation mechanism. this mechanism seeks reducing the packet collision, but actually checking the availability of the resources that the vehicle has selected. And this concept of selected is important to understand the operation of the revaluation mechanism. A selected resource is a resource that the vehicle has not yet announced. As I explained before, in this SPS mechanism, the vehicle is first selecting a resource, and then in a chain-like process, each transmission is going to announce transmission, future transmission, and reserving those resources. The revaluation mechanism can only act over selected resources, so those that has not been announced yet. And actually, the operation of the revaluation mechanism starts by what is called the revaluation check. And let's consider in this example that a vehicle has initially selected a resource, but sometime before performing the transmission in this selected resource, the vehicle is going to check whether this resource is still available or other vehicles have reserved the same resource to perform the transmission. If the vehicle detects, know that now the resource is marked as excluded resource. If the vehicle detects that this resource is not anymore available, it is detected a revaluation, and then the vehicle has the option to replace the initially selected resource by another resource that has not been excluded in this new selection window that is created once the revaluation process starts. So in principle, with this mechanism, the vehicle has avoided a potential collision and has selected new resources where to perform collision-free transmission. This revaluation check, as I said before, should only occur once in every reselection counter transmission, so when the reselection counter depletes. However, the transmission in selected resources, as I'm about to explain, augment when the vehicles are handling aperiodic traffic and of variable size. So basically, this is happening when the reserved resources do not fit the current packet to be transmitted. So this is going to make the mode 2, the semi-persistent scheme, more unstable and more prone to packet collision. Let me show you with some examples what do we mean with this instability and why more transmission are performed in selected resources and aperiodic traffic of variable size. The first case happened this is what we call size reselection. Let's consider that a vehicle has selected a resource at this point in time to transmit a 200 byte packet, and it performs a reservation to transmit later another packet. But the packet that is generated later is bigger inside, and then it cannot be fit in this reserve resource. So a new selection is needed. And then the transmission that was going to be performed in a selected resource, in a reservation, is now performed in a selected resource. We can also see that because of the aperiodic nature of the traffic, a vehicle that has a reserve resource at this point in time might need to do a resource reselection because of the generated traffic requires that the packet is transmitted before this reserve resource happen, and then it performs a new resource reselection within the limit of the packet delay budget. And something else that might happen is that in this example, the reservation actually is happening before the packet is generated. So this reservation is not utilized. Then this transmission is not happening. It's not announcing a following transmission. and the vehicle might use these resources, but they have not been announced, so these are not reserved resources anymore. So what we have studied is whether the instability that has been created by this message variability on the semi-persistent scheduler scheme can be handled by the reevaluation mechanism that is used in 5G and V2X. We have performed some studies using a simulator that we have developed that is fully standard compliant, and also following the 3GPP evaluation guidelines in terms of a scenario like a highway with 3 lanes in each direction, considering different vehicle densities and speed included in these guidelines, and also the traffic models available in 3GPP that include periodic traffic of fixed size, in this case 190 bytes, and an inter-packet arrival time between of 20 and 100 milliseconds. It also meet the packet delay budget, and aperiodic traffic that follows an exponential random process, and also aperiodic traffic of variable packet size that is uniformly distributed between 200 and 1,200 bytes in a 200 bytes step. The other details at the physical and MAC layer are reported in this slide. I will go briefly through them. Basically, we use a fixed coding scheme that results in that the set of packets that can be transmitted in our evaluation occupied from 1 to 4 subchannels. We are considering a 20 megahertz channel bandwidth that, based on the subcarrier spacing considered, use 4 subchannels of 12 RRBs each. And at the MAC layer, some of the configuration include the definition of the sensing window, taking into account 2,200 slots, or what is equivalent in time like 1 second of a bit more than 1 second of the previous transmission of other users. The reevaluation check is conducted 5 slots prior to the actual transmission of the packet. And we also define 2 different strategies to set the reservation interval value. One where the value is set to the average RRI value, that is the average inter-packet arrival time, and one set to the minimum inter-packet arrival time, with the idea of minimizing the latency reselection that might happen. So our evaluation first comparing the results obtained when vehicles handle periodic and aperiodic traffic of fixed size. And we are doing the comparison using as a metric the packet delivery ratio as a function of the distance between the transmitter and the receiver. Here I'm reporting the results for 2 different scenarios with an inter-packet arrival time of 100 milliseconds and 20 milliseconds. So here much more frequent packets are generated. First, for a vehicle density of 25 vehicles per kilometer. So what the results are showing is that the performance of the semi-persistent scheduling scheme is slightly better in this scenario with when the vehicles handle periodic traffic than when they use aperiodic traffic. And the differences actually increase between periodic and aperiodic when the traffic intensity, when the amount of traffic increases. And as we can see, when we also include the vehicle density, the differences between the performance when vehicles handle periodic and aperiodic traffic also increases. We have been investigating why this difference between periodic and aperiodic traffic. One of the main reasons is that with periodic traffic, the reselection counter always depletes. This is what we measure with this reselection counter depletion ratio. Basically, this provides high stability to the resource selection process, since the resources are always announced and other vehicles are going to be aware of the reservation made by the vehicle. However, when the vehicles handle aperiodic traffic of fixed size, and for this particular RRI strategy, we can see that the reselection counter depletion ratio is very low. It's close to zero, basically because of the high number of latency reselection caused by this aperiodic nature of the traffic. And as I said, another strategy to actually reduce the latency reselection is to use a minimum RRI strategy. In this case, the reselection counter depletion ratio increases depending on the scenario. The latency reselection decreases as well, but then the number of unutilized reservation increases significantly, causing again this instability in the system. So in this figure, we report now not only the results for the periodic and aperiodic traffic with a fixed size, and also with the minimum RRI strategy that we see that improve with respect to the average RRI strategy, but the result also for the aperiodic traffic of variable size. And as we can see that the performance degrades when vehicle handle this aperiodic traffic of variable size, because of the size reselection that are also happening in this case in the scenario. So something we were investigating is whether the revaluation mechanism was actually detecting this collision and avoiding them. And what this figure are reporting is the packet collision ratio as a function of the distance between the transmitter and the receiver for the same scenarios as reported before. And as we can see is that for the case of aperiodic traffic and of variable size, the packet collision ratio is high, and it is not reduced as expected, despite the fact that the revaluation mechanism is used. Some numbers to show that revaluation mechanism is used shows that, for instance, that 70% of the packets are being checked for revaluation. This means that this is for this particular scenario, that 70% of the packets are transmitted in selected resources. And actually, the vehicle is detecting collision in close to 30% of the packets. But despite doing this chain of the resource, once the collision has been detected, we can see in the results that the collisions are not avoided. So with this, I will conclude this talk. In this presentation, I have introduced the new functionalities used in 5G V2X to support advanced V2X services that includes some mechanism for more dynamic management of the resources and more flexibility at the physical layer with this introduction of the numerologies. We have also seen some coexistence mechanisms that are defined to allow the coexistence of both the Elche V2X and 5G V2X. We have also evaluated even some of the new functionalities introduced in 5G V2X that have shown that the high instability created by the aperiodic traffic of variable size cannot be fully handled, it's still challenging that the 5G radio V2X. Some work need to be done to optimize either this reevaluation mechanism or new mechanism need to be introduced in order to handle this instability and optimize the 5G NR V2X performance when handling this traffic. For those of you that are interested in this work and related ones, here I'm reporting some related work that you can easily find on IEEE Explore. Please, if you have any doubt and you wanna reach out to us, feel free. You have our emails in this slide, and we will be more than happy to assist and to potentially collaborate with you. Thank you very much.
Thank you so much, Dr. Baldomero, and thanks to everyone else for listening. Just to highlight a little, like, my name is Taimoor Abbas, and I am IEEE VTS Young Professional Liaison, and also serving as Young Professional Subcommittee Chair. So I have a couple of announcements to make before we proceed to the discussion. So first one is that we are actively looking for young professionals who are VTS members to volunteer and contribute to the Young Professionals Committee. So if you are interested, you are welcome to contact me. And how you must be thinking how you can contact me. I'm writing down my email address here. So feel free to drop me an email if you are interested. You can also look for more activities and events on IEEE VTS page, and there is one dedicated page for young professionals. And your suggestions are also welcome. And the last thing is that we will be posting this recording on VTS YouTube channel, so you can share it with your students or colleagues if they are not present today. So with that, we proceed for the discussion. We have a few comments from a participant named Dick Roy. So Roy, if you're here, please unmute and you're welcome to ask directly from the speaker. Thank you.
I'm happy to do so. I'm just finishing up typing in a last question, which is probably the most important one. I'm hearing that there is some belief that this technology that you're talking about makes sense. I'll just use the word makes sense for deployment in V2X ITS scenarios in which cars and people and bicycles are driving around and trying to prevent from getting killed. If you believe that that's true, can you tell me why? And the reason I ask is because I can go down to my local Fry's electronics store and for $20 buy a jammer and put it up around an intersection and take this entire communication system down. And automated vehicles and bicycles and pedestrians that rely on it will start killing each other. Why do you think this is a good idea? That's my first question.
Thank you, Dick, for your question. I mean, this goes beyond the technical aspect I have introduced here. Of course, I see your point on the possible vulnerabilities of any wireless technology, but this might not only be restricted to V2X, but for any other cellular technology. Wait
a minute. I'm not addressing cellular. This is not a cellular technology. Okay, and that's really important for everybody to understand. When we talk sidelink, there is nothing cellular about it at all.
You mean because the information that's
derived from a cellular technology, which is the fundamental problem. However, that doesn't make it a cellular technology. There is zero probability of a system getting deployed where vehicles talk to pedestrians, bicyclists, etc., that also includes an E node B or a G node B. Not going to happen. There's not enough capacity in the entire RF spectrum for that to work. So let's just disabuse ourselves of the notion that a cellular communication link is involved in this saving of life and property, broadcasting BSMs, CAMs, cooperative reception messages, cooperative cruise control, all of the things that we want to do and deploy in this system, okay, do not require, cannot require E node Bs. Unfortunately, with this choice of technology, they do require precise, and I mean precise, time synchronization. And the time synchronization that you didn't discuss it, but it's sub 100 nanoseconds. And if you don't have synchronization to sub 100 nanoseconds, lots of very interesting and bad things are going to happen in the communication links. They're not going to work. And that's why, and jamming them is just trivial, okay? This system is right. I'm just curious. This seems to be something that people don't even address. They just assume that this is all going to work perfectly. I can guarantee you that every plug test run to date on release 14, 15 equipment, that's all that we have. We don't have anything, we don't have 5G new radio yet. Every one of them has had units sitting on tables that cannot communicate with each other when one of the units unplugs the GPS simulator. All it takes is one unit to unplug, and all of the rest of the units cease to communicate because they no longer get a valid GPS waveform. And this has happened in every plug test. It's so obvious that the system is, number one, so fragile. And as your simulations point out, and they didn't even get to the real details of what happens when you actually try to deploy this in the real world, it's incredibly inefficient. It's provably a very bad choice for the system requirements of V2X. Varying message sizes at varying rates with varying priorities. Emergency brake messages that have to get out, that can't, because there's no resource available. It's just provably bad. And many of the work that has been done, and by your university as well, has indicated this. Yet, there is still this thinking that this is a good idea. I'm just wondering why. Why do people hold on to the meme that this is a good idea? Do you have any idea?
Well, thank you, Dick, for sharing all your thoughts. I think the discussion about this is maybe out of place for this presentation. I'll be happy to share my personal ideas on this, but today my goal was mostly to show to the community what are the features that this technology has introduced, the novelties with regards to LTE V2X, and some studies that we are conducted, in particular with one of the mechanisms that was introduced in this technology to show how it's working and how the community could actually take this result to show there's still some work to do to handle this traffic that vehicles might generate, and that are not always periodic, that has other properties and like periodicities and variable sizes, and that there's still work to do there to actually make this system reliable and to handle efficiently all this traffic. But I really appreciate your thoughts on this.
Yeah, I've been involved in this since its inception. And by this, I mean ITS. So, just for the sake of the people on this call, I wrote most of 802.11p. I was involved in BD. This goes back 20 years. Okay. So I'm well aware of exactly how all of this came about, including why we are even having these discussions. And I'm not going to go into those details, okay, because it's inappropriate on this call.
Thank you.
But the world needs to know, and they need to ask this very fundamental question: why are we even having these discussions? Okay. In Europe, you well know that there are over 1 million vehicles on the roads today with G5 802.11p that work very well. Tens of thousands of roadside units deployed that work very well. Unfortunately, here in the US, for a very specific reason, we've had to, quote unquote, turn them all off. It's mind numbing. Okay. People are dying on the roads. They didn't have to be. We were deploying the system 7 years ago.
Well, thank you.
It was being deployed.
As I said, this is maybe
Yeah.
not the place for this discussion, but thanks a lot for your thoughts.
Thank you. So we can take one or two more questions. We are already above time, and thank you, Dick Roy, for valuable input. And then we move on to just a couple of more questions are here. So first one is from Samuel. He's asking, does 5G NR V2X uses licensed or unlicensed frequency bands? And how are the authentication and securities handled?
Well, there are, as I said before in one of the slides, 5G NR V2X is designed to operate in two main frequency bands, including the ITS band that is unlicensed. So yeah, the question, the answer would be that it could operate in both of them, in licensed and unlicensed. Regarding the association process, it's not happening for this distributed cycling communication. So let me try to go to this slide first. Here. So as I was saying, this particular band, the M47, is the unlicensed ITS band that is being used for other technologies, as Dick was mentioning before, like ITS G5 based on IEEE 802.11p, but also for other LT-based technologies like V2X. What 3BP is defining is the possibility to use a licensed spectrum, like the one that is being used for UU-based communication, so communication with the base station, also for cycling transmission. This includes so far these three other frequency bands.
I think it's important to note that the ITS band that you're referring to, the 5855 to 5925, is not an unlicensed band in the sense of the word that it's an ISM band. Okay.
It's reserved for
Exactly. Yes, it is reserved for specific
ITS.
using specific technologies.
Mm-hmm.
And in the US, it is a licensed band. Okay. So yeah, we lost the lower 45. So, but the upper 30 is still licensed. You license by rule the OBUs, but you are required currently to get site license for RSUs. All DSRC RSUs, you have to go to the FCC and file for a license. Okay. And that's still true of the V2X units that are going to be trialed under what's called a waiver process, which has yet to be announced. So your slide that says 30 megahertz reserved for V2X is not really true. Now, so the upper 30 is in limbo. The lower 45 has been given to the Wi-Fi guys. That has happened, sadly, but that's a whole nother story. Just so people are aware, there are no rules today in the US that mandate the use of V2X. None. V2X does not appear in any FCC regulation at all. Okay, just so people are aware of that. It's a common misunderstanding. Okay. So you're not alone. A lot of people think that V2X has been reserved for the US. No, it has not. That is not true.
Correct,
Yeah.
correct.
And you can read the
Okay.
rules, they're online. You just go to the FCC website, read the rules. Yeah, you'll see no mention of V2X at all in any rulemaking.
Yeah,
It
so
is.
far we have
Okay.
nothing.
Mhm.
But maybe we see something happening at least in the coming years. But right, as for today, there is it is as you mentioned. So we have one last comment or question it is, and then we can close the call for today. But it's what about using adaptive modulation and coding instead of using 16 QAM?
This is a very good question, actually. Let me go to one of the slices where I showed some of the issues that happen when handling aperiodic traffic of variable size, and see what effects might have the use of adapted modulation and coding scheme. One of the things I mentioned was that in this specific case here, where size reselection is happening, is because 600 byte is generated and cannot be fit in this reserve resource that was first created to transmit at 200 bytes. This is the case while we keep using the same adaptive modulation and coding, the same modulation and coding scheme used before. An alternative here would be to use a higher order modulation and coding scheme and then fit these 600 bytes into this reserve resource. That can happen actually, but we might take into account as well that by increasing this adaptive, this modulation and coding scheme, we are sacrificing also the protection of the performed transmission. So trying to solve an issue of making a new reselection process, maybe we are creating another issue of performing a less robust transmission because of this adaptation in the modulation and coding scheme.
Yeah, I think the answer to this question is there is adaptation here. It's amongst a fixed set of possibilities, a finite set, but that finite set is very large. If you look at the MCS tables in the ETSI standards, there are a lot of them. However, in fact, they're up to 31 of them. Many of them are not useful in the V2X environment because of Doppler effects and other issues. So you will see that in the ETSI standards and in the US standards, they restrict the MCS schemes to be generally less than 11. In the US, we don't use 8, 9, and 10. So you have up to 8 modulation and coding schemes that you can be used here in the US, and they have 12 in Europe currently for 14. Okay, 14 and 15. Nobody's doing 16, 17, or 18. So 5G new radio is not on the table right now. Okay, so but they do, and what you do sacrifice when you go up in your module MCS is you sacrifice essentially range, because you do one of two things: you either code less, channel code less, or you up the constellation. And when you do either of those, your receiver's quote unquote sensitivity goes down. You do numerically down from like -103 to like -188, algebraically up. Okay, and you don't get the range. It's that simple, and that's a problem.
Yeah, you are right. You don't get the range. I mean, we haven't talked about the range requirements, right, but of course it will depend on the requirement of the services.
Exactly. Yeah. So I mean, it's a very complicated thing. However, there is quote unquote adaptive modulation. It's not continuous and it's not very fine grained, but you do have a finite set of MCSs from which to choose. And mostly they're QPSK. However, there are some 11 and up are 16 QAM, MCS 11 and up, and they are allowed. So you have 16 QAM, QPSK, and oh, by the way, the SCI blocks are always sent with MCS 0. So that's the other thing you have to remember.
Yeah.
Okay. Control blocks are always set at the lowest MCS. I mean, for obvious reasons. And that has to happen.
Yeah.
I have a quick question on your slide where you talked about the simulations of, and you had 4 subchannels in 20 megahertz. And each subchannel had, I think, that one there. Can you fill me in on 20 megahertz, the third bullet, 20 megahertz channel bandwidth, 4 subchannels of 12 resource blocks each. Now, in release 14 and 15, that we only have 15 kilohertz subcarrier spacing. And so these resource blocks are 180 kilohertz wide. And, so each 12 resource block subchannel is 2 megahertz wide. And so if I only had 4 subchannels of 12 resource blocks, and under those conditions, I would only be using 8 of the 20 megahertz. I don't think you mean that here. So what do you mean by 12, the resource? How do you fill out 20 megahertz with 4 subchannels of only 12 resource blocks?
No, I mean, with this 4 subchannel and 12 resource block each, since we are using a 30 kilohertz subcarrier spacing, actually, we are filling most of the 20.
You're filling 16 of the 20.
We are filling 48 of the 51 available in 20 megahertz.
Yeah, that's right. Okay.
Yeah.
Okay.
So only 3 are.
Okay. And so each is 4.8 kilohertz wide or 4.8 megahertz wide, something like that.
Yeah. It is true, Dick, that now latest releases of ETSI for 5G and V2X are indicating that under this configuration of 20 megahertz channel bandwidth, the number of RBs that form a subchannel is not 12, but 10.
But 10, so same here in the US. And
that would make that 5 subchannels are available in this 20 megahertz. But we ran this study before this latest release of the ETSI document.
Right, exactly. Yeah, and we have the same here in the US. And the first 2 resource blocks of every subchannel. And unfortunately, they use the term subchannel to mean those 10 resource blocks, because that's not what a subchannel is. A subchannel is a concatenation of adjacent blocks of 10 subchannel of 10 subchannels. Okay, of 10 resource blocks. The first 2 of which contain control information, and the last.
This is not anymore the case in 5G new radio.
New radio does
in
it.
Elche V2X. In this case, in 5G new radio, the control information and the data is multiplexed together, and there is no anymore this separation between the control and the data information.
And that's all fine. It's a quick question for you: is the modulation still single carrier OFDM? Are they still doing SCOFDM?
Yeah.
Or are they planning? Well, release 17 was published, and I can look this up. My understanding was they were going to stick with single carrier OFDM. Is that true?
Yeah, that's the case.
It is.
Okay.
It is not changed.
Okay, so the timing requirements, are still 12 TS. Is that right?
I'm not well aware of this specific detail, but yeah, should be.
Yeah. Okay, so it's 300 nanoseconds, 391. Okay, you need to try this. You need to try this UE synchronization you're talking about. And what you're going to find is that it is impossible to maintain that requirement, okay, with cars that are driving around, because cars are more than 391 feet apart, and it's a foot per nanosecond.
Thank you a lot, Dave, for raising this.
It's this.
I'm sorry. please excuse me, I must interrupt here. We must close the call just because we are running out of time. We have one raised hand, so we can take that one, and then before we go. So we have a question from Professor Hisham, if you're here.
Okay, hello, thank you for your presentation. I'm Hisham Al-Badawi, the chair for the VTS chapter, IEEE VTS chapter in Egypt. I am asking about the two things concerning the 6G integration between the ITS and the availability of V2X as a layer, maybe for the VOG layer. What about the synchronization problem between the coordination function of the fusion center represented by the roadside in the the radio resource allocation problem? On the other hand, do you have some sort of priority scheme for police or surveillance or ambulance cars for this proposal that you are presenting in your nice presentation? Also, how could we mitigate the co-channel interference between the concatenated connected vehicles, especially in the traffic jam, maybe at the rush hours? And how could we avoid such interference and the degradation that will be happen in the quality of service? Thank you.
Thank you. Thank you. Yeah, there was a question related to synchronization, right? I guess it was the first one. And as I indicated in one of the slides, for 5G and V2X, it is using same sources of synchronization as previous LTE technology, like relying on satellites communication and also relying on synchronization that can be provided by the base station. And in addition, there is a new source of synchronization, like this SyncRef user that can also transmit timing information that other vehicle can use to synchronize. I have to admit that this is not the field of our research, this timing and this synchronization aspects, and how close this and how accurate this must be to actually operate in an efficient manner. And
so,
then,
excuse me, I'm asking
sure.
about the synchronization, because the synchronization, if you have a good synchronization and well-coordinated function between the roadside side, you can avoid more and more collision between packets, and this will improve what you call periodic V2X connectivity. So if we have strict synchronization frames, so we can avoid more and more collision, and so we can improve the overall quality of service, especially in the traffic jam in the downtown cities. Looks like a huge amount of dense urbans or something.
Yeah, thank you for your comment. Yeah, actually, in our evaluation, we are considering that vehicles are perfectly synchronized. So synchronization is not another source of problem that might happen. We actually, as you mentioned, if vehicles are not synchronized, then there might be another interference caused even though vehicles are selecting apparently free resources. And about the comment you made related to peak hours and crowded scenarios, in those cases, it's unavoidable to have co-channel interference. This is actually taken into account in our evaluation as well. Of course, it affects the interference that receivers are going to have while detecting the packets. So it's all taken into account in our studies based on 3GPP models available in the guidelines for evaluation.
Okay, thank you. And we may use some further research concerning the other channel impairment and the missynchronization problem that will affect the overall performance. Thank you for your nice presentation. Thank you.
Thank you for the question.
So once again, thanks to Dr. Baldomero, especially for taking time, and for all this, the listeners, and for the interesting discussion. I think it was quite nice. Although we are a little bit over time, I'm sorry for taking that, but I think it was totally worth it. So I will post the recording as soon as possible. Thanks a lot, and with that we can close the call.